Yes, okay. So, welcome everybody to the International Single Automorphic Forums. So today we have Hohto Bekki from the Max Planck Institute of Bonn, who will teach us about on the denominators of the special values of the partial zeta functions of real quadratic fields.
Okay, yeah, thank you very much for the introduction, and also thank you very much for giving me this opportunity to talk at this nice seminar. Okay, so I would like to start my talk, which is, the title is on the denominator of the special values. The partial zeta function of real quadratic fields. So it's about the, yes, as the title says, that it's about the denominators of the partial zeta function, a special values of partial zeta function, which are known to be rational numbers. And I study these as a small application of Carter's work on the denominator of Eisenstein homology classes. And this is a joint work with Ryotaro Sakamoto. And I would also like to share my notes, because my screen is small. I will put a link on the chat. So please use this if you miss something. Or you can also ask me questions. Okay, so then I will start with the introduction and explaining main results. So let F be a real quadratic field. For example, Q adjoins square root of 5. And let O be its order. If you are not familiar with the order, you can just think of it as the ring of integers, but we deal with a more general order. And for order OR, we let this CLO plus denote the narrow class group. Of O. Then for the narrow ideal class A, we have the so-called partial zeta function, which is defined to be the sum over all integral ideal in this ideal class. And we sum 1 over norm to the S, which is defined a priori in this region, but can be extended meromorphically to whole plane. This is called the partial zeta function. Associated to this order and the ideal class. So this is very interesting object and many things are known. So I will list some basic properties. And the following properties are also known for the partial zeta function of totally real fields. And the first property is the so-called rationality, which says that for every integer which is greater than or equal to 2, the value of this partial zeta function at -1 minus k is a rational number, which is often known as the Klingen-Ziegel's theorem. And this is for example, this is an example. Well, the example are like, for example, the value of Riemann zeta function of -1 is 1/12, or the value of Dedekind zeta function of q² 5 at -1 is 1/30, and so on. And there is a refinement of this rationality, which is often called integrality or periodic interpolation. And for safety, I would like to assume this order to be the ring of integers. And let C be the another auxiliary integral ideal. Then this integrality is the following. So if we consider the so-called C-smooth partial zeta function, which is a kind of modification of the original partial zeta function, which is defined to be the original one minus some norm to the k times the shift of original partial zeta function. And it is known that this modified partial zeta value is an integer outside the primes over this C. So this is often called integrality, and we have further refinement, which is called periodic interpolation, which is essentially, there is a periodic interpolation of these values. But I will not discuss this in this talk. But anyway, these are the known properties of the partial zeta function. And in today's talk, I would like to consider a slightly different type of integrality. So in today's talk, I would like to discuss the uniform integrality in some sense. So I will say universal upper bound for the denominators of these special values of partial zeta function, where I vary these orders and ideal classes. So as an application of Hohto's work, Hohto's theory on the denominators of Eisenstein classes. And yeah, for more precisely, for an integer k, which is greater than or equal to 2, let's consider the following set, dk, which is a set of positive integers which scales all the denominators. That is, for every real quadratic field, which I abbreviate as RQ, and for every order in F, and for every ideal classes, J kills the denominator of these partial zeta. So these J are kind of universal upper bound for these rational numbers. So this is a set of universal upper bound of these partial zeta values. And the question I would like to consider in this talk is whether we can determine this set. So And in order to illustrate this question, I would like to briefly recall one observation by Zagier. So in his early work, Zagier proved the following formula for the partial drift values, which says that the value of this partial drift function at 1 minus k can be written in the following way. So sum over some indices of some integer, which I will, I will briefly explain the notation afterwards. So I will simply write so this p j plus I is the Bernoulli number. So this is this formula where this the ikj and ai, which sit here and here, these are certain explicit integers, which is defined by continued fraction expansion of real quadratic irrational. And also this Bj is the jth Bernoulli number. Which is a rational number. Yeah, rational number. So this is the formula by Zagier, and this is very nice formula because this formula is a kind of universal formula which is applicable to every partial drift values of real quadratic fields. So, for example, from this formula we have the following corollary. It says that the least common multiple of the denominators of these rational parts gives the universal upper bound for the denominator here, because these are integers. So denominator of this part and denominator of this part gives at least one universal upper bound. So in particular, this is non-empty set, which is a priori non-trivial thing. And he also computes some examples. So if k is 2, then this least common multiple is 720, so which gives one universal upper bound. But he observes that this is not the best possible thing. And actually we can take a smaller universal upper bound, which is 120, and this is best possible. And for case 3, the least common multiple is 15120. But again, this is not the smallest one, but we have this smallest universal upper bound. And in the last part of his paper, Zagier mentioned, remarked that it is not very easy to determine the best possible upper bound from his formula. And but recently Duke considered a similar problem using his higher Radmacher symbols and gave a precise, well, better universal upper bound. as a conjecture. So I will explain this next. And in order to explain this, we set the value of Riemann zeta function at 1 minus 2k, which is also a rational number, to be n2k over j2k, where this is the numerator and j2k is the denominator. For example, the value at minus 3 is 1 over 120, and value at minus 5 is minus 1 over 152. And also sometimes we have a numerator, like it's 91 and like this. And one might realize that these numbers are exactly these minimal universal upper bound, and actually that's the conjecture by Duke. So he conjectures that this denominator of the Riemann zeta function, well, actually he stated in using his Higher-Radmann symbols that it is equivalent to saying that the denominator of this Riemann zeta function gives a universal upper bound for the partial zeta values of real quadratic fields. In other words, this J2K kills the denominators of every partial zeta values of real quadratic fields. And so then I can explain our main result. So the main result I would like to explain in this talk is the first, the Duke's conjecture is true. And moreover, his upper bound, which is the denominator of the Riemann zeta function, is actually the best possible one. And in other words, this set of universal denominators are just the multiple of this denominator of the Riemann zeta function. So this is the main theorem today, and there's one remark that the Duke's conjecture is also proven by O'Sullivan. Using a more direct method than the proof, which I will explain in the following. So this is what I want to discuss in this talk. So I would like to start explaining the strategy of this proof. So there are several ingredients. The first one is the integral representation of the partial zeta values. And its cohomological interpretation. And the second ingredient is, as I said, how does it work on the denominator of the Eisenstein classes. for SL2C. And in order to prove this minimality of Duke's upper bound, we need a little more work, which is actually very basic of the so-called Hida theory. And so these are the main ingredients in the following proof, and I would like to explain each of these things. So I will start with this integral representation. And I would like to start with this Eisenstein series. So let E2K be the Eisenstein series, which is normalized in this way. So this is the holomorphic Eisenstein series of weights 2K. And then the integral representation I would like to explain is the integral representation using this Eisenstein series. So integral representation. This is often called the Hecke's integral formula. And I would like to explain this in a very specific case where the real quadratic field is Q square root of 5 and the order is its maximal order. The adjoint 1 plus square root of 5 over 2. And the ideal class is the identity because this is PID. And in this case, the integral representation of this partial zeta function is the following. So let tau be any point in the alpha half plane. Then we consider the integral from tau to 3 tau minus 1 over tau of some quadratic polynomial. To some power and Eisenstein series. Then it is known that this integral of Eisenstein series becomes some sign times this partial zeta value divided by the Riemann zeta value. And this is a very nice formula. And one very nice thing is that this is not only an analytic formula, but it has a cohomological interpretation. So namely, so because this 3 tau minus 1 over tau is not a random point, but it's a translation of this tau by some hyperbolic element. Whose eigenvalues are I think these real quadratic irrationals. So this domain of integration defines a certain closed path on the modular curve. So this defines the first element in the first homology of the modular curve. This part defines the first homology with some coefficient, which I will denote by m2k minus 2, where this is the 2k minus 2 symmetric product on which we have a natural action of SL2Z. So in the following, I would like to denote by gamma this SL2Z, and also by y this modular curve. So in anyways, this part defines homology, and also this Eisenstein theory defines a certain one form, a holomorphic one form on the modular curve. So it defines the homology class. Again, with some coefficient, which is a dual of this original one. But also, because this is an analytic function, it defines the homology class over C a priori. So where this check means that it's the dual gamma module of M2K minus 2. And then this integration can be interpreted simply as the pairing between the homology and cohomology. So in this way, we have this a very nice cohomological interpretation of this integral representation, and also the cohomological interpretation of these zeta values. And yeah, actually, more generally, we can do this exactly the same thing for every ideal classes. So I would like to briefly explain this. But first, let me denote by this I to k minus 2, this homology class defined by the holomorphic Eisenstein series of weight 2k. Then, as I said, for each ideal class A of some number real quadratic field and some order in this real quadratic field, we can associate certain integral homology class, which is defined in the same way as this one. That is, well, very roughly speaking, this ideal class defines some geodesic on the upper plane connecting to real quadratic conjugate real quadratic irrationalities, and then this geodesic defines a certain hyperbolic element which fixes this geodesic. Then this class can be simply defined by the integral path from tau to gamma tau of weighted by some gamma invariant polynomial to some power. So this is a very rough explanation, but yeah, anyway, we can define some homology class here, and in the same way as above, we can prove that this pairing between the Eisenstein class and this homology gives us the partial zeta value. So the pairing between this Eisenstein class, yeah, this is called the Eisenstein class. And the pairing between this Eisenstein class and this cycle gives the partial zeta value over Riemann zeta value. And if you call the a notation for the numerator and denominator of Riemann zeta value, this can be written as like this. And if you also recall the statement of Duke's conjecture, it is exactly about this part. So this denominator Riemann zeta value times this partial zeta value. Therefore, in principle, in order to understand this part, it suffices to study this Eisenstein cohomology class and this cycle. And this Eisenstein cohomology class is studied by Hohto. So I would like to explain what the work of Hohto. And its relation to Duke's conjecture. So Hohto studied these cohomology classes, Eisenstein cohomology classes, and found the following theorem. Actually, this is unpublished work. But I was able to learn this from Hohto. Which says the following, but the zeroth part is the classical thing which is known before Hohto. So, which says that this Eisenstein class, which is a priori defined over a complex number, is actually defined over a rational number. So this is the rationality of this Eisenstein class. And then we can think about the denominator of this rational class. So the denominator of Eisenstein class is defined to be the minimal positive integer, which makes this Eisenstein class integral. Up to torsion. And it is known that this has many applications to number theory. And Hohto found the following very precise formula for this denominator, which says that the denominator of Eisenstein class is exactly the numerator of the Riemann-Zeta value at 1 minus 2k, which is denoted by n2k in this talk. So I would like to remark on the meaning of this theorem very briefly. Well, at least so one aspect of this theorem is that if you recall the definition of this holomorphic Eisenstein series, then you may find that the denominator of holomorphic Eisenstein series as a Q series is exactly this numerator of the Riemann-Zeta function, numerator of Riemann-Zeta value, because here this is integer, so the denominator of this Eisenstein class is coming from the numerator of this Riemann-Zeta value. On the other hand, what Hohto's theorem says is that this is also equal to the denominator of this Eisenstein class with respect to the integrality of integral structure of Betti homology. So this is about the integrality with respect to Betti integral structure. On the other hand, in some sense, this denominator for Q series is related to the Durham integral structure. So what Hohto's theorem says is that the integral structures in the Durham sense and the Betti sense coincide on the Eisenstein part. So this is the easy part, and this is the hard part. And yeah, this is one interpretation of this theorem. But anyway, for using this theorem, we can already prove Duke's conjecture. because the Duke's conjecture says that this denominator of the Riemann zeta function kills the denominator of partial zeta function, partial zeta values. So, in other words, Duke's conjecture claims that this is integer, but from the integral representation of these partial zeta values, we already seen that this is the pairing between Eisenstein class and this homology class. So before we had this denominator was here. And by Hohto's theorem, what we know is that this is the denominator of Eisenstein class. So this is integral. So this is integral homology class, and this is by definition it is integral homology class. So this is integer, and this gives the first part of our main theorem, which is Duke's conjecture. So now, in the remaining time, I would like to explain the latter half of our main theorem, which is about the minimality of Duke's upper bound. So, and in order to explain this part, I would like to briefly summarize the previous argument. So first we have this homology class, first homology of modular curve. Sorry. And we have a map induced by taking the pairing with Eisenstein homology class, which a priori goes to C. But what Hohto's theorem says is exactly that the image of this map is 1 over n2k times Z. So this surjectivity is Hohto's theorem. And on the other hand, we have seen that we have a map from this narrow ideal class group to the first homology, which sends the ideal class to some cycle, which we denote by ZAK. And for later convenience, although this is simply a map of sets, that I would like to make it into homomorphism. And I would like to denote this DK. Then the integral representation of partial zeta value says that the image of this integral, image of this ideal class along this composition is this number. I think it's this one. Therefore, we have seen that this part is inside Z. So this is the Duke's conjecture. But in order to prove that this is the best possible irreversible upper bound, this is equivalent to saying that this part generates the whole V if we vary the orders and the ideal classes. So the minimality of this Duke's upper bound is equivalent to the composite of this map, which we denote by pi, is surjective. Therefore, if this map zk, which assign each cycle from ideal class, is surjective, so if zk is surjective, then since this is also surjective, this is surjective, so we are done. However, it seems that this is not true in general. So, well, at least we couldn't prove the surjectivity of this zk. So, we have to do something instead. So the solution is, so instead of proving the surjectivity, prove that the image of this zk generates sufficiently large subspace. Of this homology. So because if we can prove that this image is sufficiently large that this, yeah, so we want to prove that the image of this map is sufficiently large so that we can show that this is surjective. And in practice, this sufficiently large subspace is actually the so-called p ordinary part. So first of all, in order to prove the surjectivity here, it suffices to show that this is surjective after tensoring Gp for every p. So this is equivalent to showing that this is surjective for every p. And since we have a Hecke operator acting on this, sorry, this is homology. This is not homology. Since Hecke operator is acting on this homology, we have a so-called very nice subspace, which is called p ordinary part. And so our strategy is to prove that the image generates this p ordinary part. And in the remaining time, I would like to end this talk by explaining the outline of this last part. So for simplicity, let's assume, I would like to assume that p is greater than or equal to 5. And also let y1p denote the modular curve of level gamma 1p. Then we consider the following diagram. Actually, we will do some diagram chasing. So first of all, what we want to prove is the following. So we have this homology of modular curve. It's tensored by Zp. And this goes projectively to this space. This is by Hohto's theorem. And we have a map from the set of narrow ideal class groups. And what we want is the surjectivity here. And as I mentioned, in order to prove the surjectivity here, it suffices to consider the so-called ordinary part, where, well, I'm not going to explain in detail about this ordinary part, but it's roughly speaking, the Hecke operator is acting on this space, and we have the so-called ordinary projector, which is defined by taking a limit of this iterated Hecke operator. And this ordinary part is simply the projection of this usual homology under this ordinary operator. And what we want to prove is the kind of surjectivity here. But in order to work with the ordinary part, actually, it is more convenient to go to the level P. So we first lift everything here to level gamma 1P. So also in gamma 1P, we can define a similar map as the one which I explained before. And we denote by CK of gamma 1P. And we can also show that this is surjective. So therefore, it suffices to show the surjectivity here. And in order to show the surjectivity here, it suffices to show the surjectivity after mod P, because this is finite generated ZP module. Then there's a kind of miraculous thing for these mod P homology, which is often called Hida's contour theorem. That is, we can actually vary the weight after mod P. So we can prove the isomorphism between the homology of coefficient ZP and coefficient this gamma module. Then we have the similar thing again for this this homology with Z over P coefficient. So in some sense, we can interpolate this weight after considering mod P. Then, as I said, this is the case for constant sheaf. And for the constant sheaf, we can prove the surjectivity here. Because the homology with constant sheaf is basically very simply the cycles on this modular curve. And therefore, by summarizing the arguments, we can show the surjectivity first here, then it is surjective here. And actually, this is slightly not commutative, but it's actually almost commutative. So we pretend that it's commutative. Then since this is surjective, this is surjective. And since mod P is surjective, then this is surjective. And therefore, this is surjective. And because this is surjective, this is surjective. So by doing this type of diagram chasing, we can show this surjectivity and which proves the main theorem. And yeah, although I have still time, this is all I wanted to talk. So thank you very much for listening.